You want your kid to learn coding, but you're not ready to hand them more screen time. I get it. I'm Dr. Priya Mehta, a child developmental psychologist who specializes in how screens affect young brains, and I've spent years studying how kids can learn real programming concepts without ever touching a tablet or computer. Turns out, there's a whole world of toys that teach the exact same logic, loops, and debugging skills that actual software engineers use, all through buttons, tiles, and physical robots, and they work better for young learners than screens do.
You're listening to the STEM Lab podcast. Quick note before we get started. Everything you're about to hear, the research, the recommendations, the developmental psychology behind it, that's all verified and written by real human experts. The voice you're hearing, though, that's AI generated. Just wanted to be upfront about that. Now, if you've been listening for a while, thank you. Seriously, it's great to have you back. And if you're new here, welcome. We're really glad you found the show. We release new episodes every Monday, Wednesday, and Friday, covering practical STEM education, coding tools, developmental milestones, all the stuff that actually matters when you're trying to teach your kids technical skills at home. So let's jump into today's topic, screen-free coding toys and how they work.
Screen-free coding toys are physical learning tools that teach programming fundamentals through tactile interaction rather than digital screens. We're talking about sequence, loops, conditionals, debugging, algorithmic thinking, all taught through things you can touch and move around. These tools include programmable robots that follow button press commands, board games that simulate computational processes, wooden maze builders that work like logic gates. The range is pretty wide. Now, screen-free doesn't mean anti-technology. It means the primary interaction happens through physical objects. You're pushing buttons on a robot's back, placing directional tiles on a game board, snapping together command blocks, arranging magnetic coding pieces. Some of these tools do include optional screen-based extensions, but their core functionality lives entirely in the physical world. What makes these legitimate coding education rather than just puzzles? They map directly to concepts used in industry-standard programming languages. When your 5-year-old arranges arrow cards to guide a robot through a maze, she's writing an algorithm. When your 7-year-old discovers he can use a single repeat tile instead of 4 individual command cards, he's implementing a loop. That's the same efficiency principle that drives Python functions and JavaScript iterations. Let's talk about how these toys actually work mechanically. Most screen-free coding toys follow a program then execute model that mirrors how real software development works. Your child creates a sequence of instructions using physical components, then activates the toy to run the program and observe results. Here's what that looks like in practice. Button-programmed robots, something like the Botley 2.0 activity set, store up to 80 commands in memory. Check the show notes for a link to the current price. Your child presses directional buttons on a separate remote, forward, backward, left turn, right turn, building a command sequence one step at a time. When she presses go, the robot executes each instruction in order. If the robot crashes into a wall instead of reaching the target, she debugs by reviewing her button sequence, identifying the error, clearing the program, and trying again. This cycle, write, test, debug, revise, that's software development distilled to its essence.
Tile-based systems use physical cards or blocks representing commands. ThinkFun's Robot Turtles uses direction cards like forward, turn left, turn right, and a special laser card to clear obstacles. Your child arranges cards in sequence on the table. You, acting as the computer, move the turtle piece according to each card. Your child sees immediately whether the sequence solves the puzzle. The Code and Go Robot Mouse activity set, check the show notes for pricing, adds a maze grid where children place walls and cheese targets, then program the mouse's path using directional cards before pressing the mouse's back to execute. Construction-based coding embeds programming concepts in physical building. Osmo coding blocks use magnetic tiles, things like move, jump, repeat, quantity numbers, that children arrange in sequences while a tablet camera reads the physical arrangement. Though the screen acts only as a mirror reflecting the physical program, not as the primary interaction surface. Now, effective screen-free coding toys scaffold complexity through expandable challenge levels. Early challenges might require only sequence: do step A, then B, then C. Intermediate challenges introduce efficiency constraints, solve the puzzle in under 10 commands, that forces your child to discover loops. Advanced challenges add conditionals: move forward if the path is clear, else turn right. This progression matters because it prevents the cognitive overload that happens when children encounter loops, functions, and conditionals simultaneously in screen-based coding platforms. Physical toys let you isolate one concept at a time. Your child masters sequence over days or weeks, building automaticity. Then you introduce the repeat tile, and she experiences the elegant efficiency of loops against the backdrop of solid sequential thinking. Debugging becomes visceral with these tools. When a screen-based program fails, the error exists in an abstract digital space. When a physical robot crashes into a wall, your child sees the moment the program diverged from intention. She can replay the sequence, pause at the error, physically manipulate the failed step. This tangible cause and effect relationship builds debugging confidence that transfers beautifully when she eventually moves to text-based languages. From a developmental psychology perspective, screen-free coding toys leverage concrete operational thinking. That's the cognitive stage, roughly ages 4 through 11, when children understand concepts best through physical manipulation rather than abstract reasoning. When your child programs a robot by pressing buttons, she's building a mental model of sequence. The button presses leave no visual trace, so she must hold the program in working memory, visualizing each step. This strengthens executive function skills: planning, working memory, inhibitory control, resisting the urge to just press buttons randomly.
When she uses physical tiles arranged on a table, she can see the entire program simultaneously, a visual representation of algorithm structure that mirrors how professional developers read code. She can identify patterns. Hey, I'm doing forward 3 times in a row. Recognize inefficiencies, and physically restructure the program by moving tiles. The physical manipulation activates motor memory pathways that pure visual learning misses. Research on embodied cognition shows that gestures and physical actions during learning create stronger memory traces than passive observation. Your child who physically turns a robot left by pressing a button is encoding that left turn concept through multiple neural pathways: visual, motor, spatial, and linguistic. Moving on to why this matters for your child specifically. Let me be direct. I don't advocate zero screen time. Screens are tools, and your child will eventually need digital fluency. But the current average of 6+ hours daily screen exposure for children aged 5 through 8, according to American Academy of Pediatrics data, that's not building skills. It's displacing physical play, conversation, hands-on problem solving. Screen-free coding toys let you say yes to programming education without adding to screen time totals. Your child gains legitimate computational thinking skills through the same kind of physical play that's always supported cognitive development. You're not restricting, you're offering a guilt-free alternative that happens to align with how young brains learn best. I've seen parents dismiss physical coding toys as cute but not serious. Here's what changes their minds: watching their 8-year-old transition to Scratch programming and immediately understand loops because she spent 6 months using repeat tiles with a floor robot.
The skills screen-free coding builds are foundational. Algorithmic thinking, breaking complex goals into step-by-step procedures, debugging mindset, viewing errors as information rather than failure, pattern recognition, identifying repeated sequences that can be abstracted, spatial reasoning, mentally rotating paths and predicting movement, sequential memory, holding multi-step procedures in working memory. These aren't toy skills, they're prerequisites for every programming language. Your child who masters them through physical play has a cognitive scaffold that makes text-based coding feel like a natural extension rather than an overwhelming leap. There's also a social learning bonus with these tools. Most screen-free coding toys naturally invite collaborative problem-solving. When your child programs a robot on the living room floor, siblings gather to suggest routes. Parents become playful computers executing card commands in board games. Grandparents can participate without tech anxiety because the interface is just plastic tiles and wooden blocks.
Contrast this with screen-based coding platforms, which typically isolate the learner in front of a device. Even supposedly collaborative coding games on tablets create parallel play, children in the same room but each absorbed in their own screen, rather than true cooperation. The conversations that happen during physical coding, wait, what if we put the turn before the forward? Oh no, I see the bug, it's this card here. Those are language-rich, socially connected learning moments. Your child is simultaneously building computational thinking and practicing communication, negotiation, shared problem-solving. Now, let's look at the types and variations you'll encounter. Floor robots and programmable bots are the workhorses of screen-free coding, physical robots that store and execute sequences of commands entered through buttons, tiles, or remote controls. Entry-level bots, ages 3 through 5, something like Bbot or Code and Go robot mouse, use simple directional programming. They move in fixed increments, usually 15 centimeters forward per step, making spatial planning concrete and predictable. Most cap programs at 40 to 80 steps and include only basic commands: forward, backward, turn left 90 degrees, turn right 90 degrees, pause. Intermediate robots, ages 5 through 8, add sensors and logic. Botley 2.0 includes object detection. Your child can program move forward until you detect an object, then turn. That introduces conditional logic through physical experience. Some bots add line-following sensors, sound effects triggered by command cards, simple if-then sequences. Advanced programmable bots, ages 7 and up, things like Cubeto or certain models of Lego Boost, bridge into construction robotics, though Boost includes screen-optional features. These often add loop commands, function calls, save a sequence of moves as a single reusable block, more complex conditional triggers. Lab specs matter here. Battery life typically ranges 3 to 5 hours active use. Most use AAA batteries, so check if they're rechargeable compatible. Durability is critical. Robots with enclosed motors and bump-resistant housings survive years of floor play. Expandability means compatible maze pieces, challenge cards, community-created puzzle sets. Card and tile programming systems use physical tokens representing code commands to create a visible, manipulatable program structure. ThinkFun's Robot Turtles, Codemaster, similar games use durable cardboard tiles or plastic chips. The advantage here, your child sees the entire algorithm laid out spatially. She can slide tiles to reorder steps, stack them to show sequence, create parallel branches. The physical arrangement mirrors how professional developers visualize code structure. Most tile systems integrate puzzle solving. Place tiles to navigate a character from start to goal, collecting items or avoiding obstacles. Challenges scale from 10-step solutions to 40-plus step algorithms requiring nested loops. Some include special tiles for functions, write a 4-step sequence here, then call it with this token, or conditionals, if path blocked, then execute this branch.
These systems need minimal setup space, just a table surface. They have zero electronic failure points, pure cardboard or plastic. They naturally accommodate multiple learners working simultaneously on separate puzzles. The major limitation, no automated feedback. You or another child must verify solutions by manually tracing the program. Board games with computational logic disguise programming concepts in cooperative or competitive gameplay. Robot Turtles positions adults as the computer executing children's card commands. Code Monkey Island uses action selection and resource management to teach planning and optimization. Code Master is a solo logic game where you program a character's path through increasingly complex grids. What distinguishes these from simple maze games? They explicitly teach programming vocabulary and concepts. Game rules use terms like function, loop, subroutine. Mechanics reward efficient algorithms over brute force solutions. Scoring often reflects code elegance. Fewer commands scores higher than verbose solutions. Board games excel at family learning. Parents who feel intimidated by teaching coding find comfortable footing in structured game rules. The cooperative format removes performance pressure. Everyone works together to debug the failing program. Certain building systems embed computational thinking without explicit coding framing. Gravity maze toys teach sequential cause and effect. Marble Run builders require spatial planning and debugging. Cubetto, though technically a robot, feels more like a wooden puzzle toy. Children insert colored command blocks into a physical control board, making the programming process feel like construction play. These tools work well for children who resist explicitly educational toys or who need sensory-rich, open-ended play. The computational thinking emerges naturally from the physical problem-solving rather than being declared as the learning objective. Let's talk about building a progressive learning path for your child. Age ranges on packaging are rough guidelines, but skill readiness matters more. A 4-year-old with strong spatial skills and pattern recognition may thrive with tools labeled ages 5 through 7, while a 6-year-old new to structured problem solving needs entry-level tools regardless of the age recommendation. Watch for these readiness indicators. For sequence-focused tools, can your child follow 3-step instructions consistently? Does she naturally describe events in order? First I woke up, then I ate breakfast, then I got dressed.
For loop concepts, does your child recognize repetition patterns in daily life? Can he count by 2s, 5s, or 10s, showing understanding that repetition creates patterns? For conditionals, does your child understand if, then, cause and effect? Can she predict outcomes based on changing conditions? If it rains, then we'll stay inside. A coherent learning path typically follows this arc. Phase 1, pure sequence, typically ages 3 through 5. Duration, 3 to 8 months. Start with tools that require only directional programming. Forward, backward, turn left, turn right. No loops, no conditionals. Your child masters holding a multi-step plan in working memory and executing it accurately. Early challenges might be 5 to 8 steps. Advanced challenges reach 20 to 30 steps. Skill milestone. Your child can plan and execute a 15-step path without external aids, recognize when a program doesn't match intention, systematically debug by comparing intended path to actual execution. Phase 2, pattern recognition and loops, typically ages 5 through 7. Duration, 6 to 12 months. Introduce tools with repeat or loop commands. Early loop challenges are simple. Move forward 3 times becomes repeat 3, move forward. The efficiency gain is obvious and satisfying. Advanced challenges require nested loops or variable repeat counts. Skill milestone. Your child independently identifies repeated sequences in her own programs and volunteers to replace them with loop commands. She understands that loops save space and reduce error opportunities. Phase 3, Conditional logic, typically ages 6 to 9, duration 12+ months. Add tools with sensors or conditional cards. If path blocked, then turn right, else move forward. Your child learns that programs can respond to environmental conditions rather than following rigid paths. Skill milestone. Your child can trace through a program containing conditionals, predicting different outcomes based on varying starting conditions. She designs programs that handle multiple scenarios with a single algorithm. Phase 4. Functions and abstraction. Typically ages 8 and up. Ongoing. Introduce tools that let your child define reusable procedures. Create a square function that draws 1 square, then call it 4 times to draw 4 squares. This abstraction ability marks readiness for text-based programming. Skill milestone. Your child recognizes when a task contains repeated complex sequences and voluntarily creates named functions to simplify her programs. This is the threshold where transitioning from screen-free coding to text-based programming becomes natural rather than jarring. One parental worry I hear constantly: if I buy this toy, will she outgrow it in 3 months? Quality screen-free coding toys scale through challenge expansion rather than replacement. Robot Turtles, for instance, officially teaches ages 4 through 8, but I've watched 10-year-olds engage deeply with the game when they create custom puzzles for younger siblings, reversing the teaching role. Look for expandable challenge sets. Products with 50 to 100 puzzle cards spanning multiple skill levels offer years of use. Bonus if the manufacturer sells expansion packs or the community shares custom challenges. Open-ended build modes. Robots that let you create custom mazes, board games with blank cards for custom commands, construction toys with interchangeable pieces stay relevant longer than rigid, single-use solutions. Backward compatibility. When you eventually add screen-based tools, choose options that integrate with physical toys your child already loves. Osmo's coding system, for instance, uses physical blocks read by a tablet camera, a bridge between purely physical and purely digital. Practical factors that parents often overlook until after purchase. Power and maintenance. Battery-powered robots need fresh batteries every 3 to 5 hours of active play. Budget for rechargeables. Some toys have non-replaceable batteries that limit lifespan to 2 to 3 years. Board games and card systems have 0 power requirements, a genuine advantage for travel and portability. Durability for repeated use. Floor robots endure crashes, drops, toddler siblings. Look for enclosed motors, not exposed gears. Bump-resistant edges, waterproof or water-resistant housings. Card games need wear-resistant coating. Laminated cards or thick plastic tokens survive years better than uncoated cardboard. Storage and setup time. A toy that requires 15 minutes of mat assembly and maze configuration won't get used on busy weeknights. Best daily use tools set up in under 2 minutes. Storage matters too. Loose pieces frustrate parents. Products with dedicated storage trays or containers actually get used. Expandability and community. Toys compatible with standard building bricks, Lego, Duplo, or generic craft supplies expand infinitely. Active user communities share custom challenges, extending value for free. Proprietary systems with no expansion options hit learning ceilings faster. Around age 8 to 10, most children benefit from adding screen-based coding while maintaining physical tools. The ideal moment? When your child has mastered loops and conditionals with physical toys and starts asking questions like, "But what if I want the robot to remember how many times it turned? Or can I make it decide which path based on what it sees?" Those questions signal readiness for variables, memory, and more complex conditionals, concepts that screen-based platforms handle elegantly. Physical tools remain valuable even after introducing screens. Many children benefit from prototyping algorithms with physical cards or robots before translating them into typed code. The tangible debugging process, moving tiles, watching a robot execute, clarifies thinking in ways that staring at error messages on a screen doesn't. Now, let's look at what to check before you buy. The screen-free label sometimes hides optional connectivity features that create unexpected friction.
Some products include companion apps that, while not required for basic functionality, unlock advanced challenges or tracking features. Others use Bluetooth pairing that works smoothly with iOS but fails with certain Android devices. Key questions. Does it require any device for setup or updates? Some screen-free robots need initial configuration through a parent's smartphone. If you're avoiding screens entirely, verify zero device operation. Are advanced features locked behind apps? A few products deliver satisfying core experiences without apps, but gate their best content behind digital pairing. What happens if the app sunsets? Manufacturers sometimes discontinue support, rendering companion apps incompatible with new OS versions. Pure physical toys have zero obsolescence risk. Offline functionality. True screen-free coding toys work anywhere. Camping trips, airplane travel, grandparents' houses. If it needs Wi-Fi or cloud features, it's not fully screen-free. Marketing copy loves vague promises, teaches coding, builds problem-solving skills. Useful specifications describe concrete capability milestones. Strong skill outcome descriptions look like this. By completing all 50 challenges, your child will plan and execute 30-step algorithms, implement 2-level nested loops, debug errors by systematically testing individual steps, create custom mazes that require conditional logic to solve. That statement tells you exactly what competency your child builds. It lets you assess whether the toy targets your child's current skill level or reaches beyond it. Vague claims like introduces computational thinking or develops logic skills could describe anything from a shape-sorting cube to advanced function definition. Demand specificity. How many steps can programs contain? Which programming concepts does it teach? Sequence only, or loops and conditionals too? What measurable skill does a child gain? Most screen-free coding toys have zero recurring costs. You buy once, use forever. But exceptions exist. Challenge card subscriptions. A few manufacturers sell base sets with 20 challenges, then offer monthly or quarterly expansion packs. Calculate total cost over 2 to 3 years before assuming a $60 toy is budget-friendly. Replacement part costs. Robots with frequently lost remotes, board games with small essential tokens, construction toys with proprietary connectors can incur ongoing replacement expenses. Check if replacement parts are available and reasonably priced. Battery consumption. Seems trivial until you're replacing 4 AA batteries weekly. At roughly $1.50 per set, that's $75 annually. Rechargeable compatible products pay for themselves within months. The best value proposition, pure physical systems with no electronics. Board games, card sets, wooden toys have zero ongoing costs. Durable robots with long battery life and abundant challenge cards offer strong cost per hour value despite higher initial investment. Children don't tenderly cradle educational toys. They drop them, crash them into furniture, spill juice on them, let curious puppies investigate them. Realistic durability for heavy use. Floor robots should survive 3-foot drops onto hardwood or tile. Anything less won't last 3 months with typical play patterns. Card games need spill-resistant coating. Construction toys need pieces that click securely but don't require adult strength force to separate. Warranty coverage. Most screen-free coding toys include 30 to 90-day warranties, but some manufacturers stand behind products for 1 to 2 years. Extended warranties signal manufacturer confidence and reduce your replacement risk. Check whether warranties cover normal wear or only defects, a meaningful distinction. Replacement part availability. A toy is only as durable as its most fragile essential component. If one directional tile cracks and the manufacturer doesn't sell replacements, the entire system becomes unusable. Prioritize products with readily available replacement parts or generic components. Let me answer some of the questions I hear most often. What age should I start with screen-free coding toys? Children as young as 3 can begin with simple sequence-focused floor robots or card matching games that introduce directional thinking. At this stage, you're not teaching coding, you're building spatial reasoning and sequential memory that form the foundation for later computational thinking. The key is matching tool complexity to your child's executive function development. Can she plan 2 steps ahead consistently? That's the threshold for entry-level screen-free coding. Starting at ages 3 through 4 with pure sequence tools, progressing to loops around 5 to 6, adding conditionals around 6 to 8, creates a developmentally appropriate path that prevents frustration while maintaining appropriate challenge. Some children show readiness earlier, others need more time with open-ended play before structured algorithmic thinking feels accessible.
Can screen-free coding toys really prepare children for actual programming? Yes, though they're foundation rather than complete preparation. Screen-free coding toys build the conceptual models that make text-based programming learnable rather than overwhelming. Concepts like sequence, loops, conditionals, debugging methodology, algorithmic problem decomposition. A child who spends 12 to 18 months working with physical coding tools develops pattern recognition skills and a debugging mindset that directly transfer when she encounters Scratch blocks or Python syntax. However, screen-free toys don't teach programming language syntax, keyboard typing fluency, or screen-based development environment navigation, skills that matter for actual software development. Think of screen-free coding as teaching musical rhythm, melody, notation reading before touching an instrument. The transition to the instrument, text-based programming, is incomparably easier with that foundation, but the instrument still requires its own practice. Are expensive programmable robots worth it, or will board games teach the same skills? Both formats teach core programming concepts, but they develop slightly different skill emphases. Programmable robots excel at building spatial reasoning, debugging persistence, immediate concrete feedback. When your child's program fails, the robot crashes into a wall right in front of her, creating unmistakable cause and effect learning. Robots also teach planning under constraints, battery life, command memory limits, physical space. Board games excel at collaborative problem-solving, visible algorithm structure, zero-friction iteration. Rearranging cards to debug takes seconds, while reprogramming a robot requires clearing memory and starting over. Board games also cost $15 to $35 versus $60 to $120 for robots, include multiple difficulty levels in one purchase, never need battery replacements. If budget allows, own both. Use board games for introducing new concepts cooperatively, then let your child apply those concepts independently with a robot. If choosing one, consider your child's learning style. Kinesthetic learners who need movement thrive with robots. Visual learners who benefit from seeing entire algorithms simultaneously excel with card games.
How do I know when my child is ready to move from screen-free coding to Scratch or Python? Watch for 3 readiness signals. First, your child independently designs complex programs using loops and conditionals without adult prompting, showing she's internalized those concepts rather than mechanically following instructions. Second, she asks questions about program flexibility that screen-free tools can't answer. Can I make it remember how many times it collected something? What if I want it to choose randomly? Indicating readiness for variables, arrays, more sophisticated logic. Third, she shows frustration with physical tool limitations rather than with programming concepts themselves. This is so slow. I wish I could just tell it what to do. Or, I want to make 100 squares, but this only has 10 repeat tiles. These signals typically emerge around ages 8 to 10 for children who started screen-free coding at 4 to 5, though the timeline varies significantly. Typing fluency helps, but isn't required. Scratch's block-based interface requires only clicking and dragging. Do screen-free coding toys work for children with ADHD or sensory processing differences? Many children with ADHD or sensory processing differences respond exceptionally well to screen-free coding because physical manipulation provides proprioceptive feedback and movement integration that screen-based learning lacks. The button pressing, tile arranging, floor play aspects channel kinetic energy into learning rather than fighting against it. However, product selection matters significantly. Children with ADHD often need immediate feedback loops, robots that execute programs instantly rather than games requiring adult participation to verify solutions, and short challenge cycles, 5-minute puzzles rather than 20-minute complex builds. Children with sensory sensitivities need tools without jarring sounds, flashing lights, rough textures. Unfortunately, many robots include attention-grabbing sounds and lights that overwhelm sensitive children. Look for products with volume controls or sound-off modes, matte finish rather than glossy plastics, and simple visual designs without excessive color stimulation. The reduced screen stimulus itself is often the biggest benefit. Many parents report that children who become dysregulated after 15 minutes of screen-based coding remain engaged and calm for 45+ minutes with physical coding toys, likely because the tools lack the rapid visual stimulation and reward schedule manipulation that makes screens particularly challenging for ADHD and sensory-sensitive children. So, where does screen-free coding fit in your child's learning journey overall? Screen-free coding toys are not anti-technology statements, they're developmentally aligned tools that introduce computational thinking during the concrete operational stage, when physical manipulation creates stronger learning than abstract symbol manipulation.
You're not choosing between screen-free coding and real programming. You're building a progression where physical tools create the conceptual scaffolding that makes screen-based coding feel like a natural next step rather than an overwhelming leap. Your 5-year-old who masters sequence with a floor robot is building the working memory and algorithmic thinking that will make Scratch intuitive at age 8. Your 7-year-old who debugs tile-based puzzles is developing the patient, systematic error analysis mindset that separates frustrated beginners from confident programmers. The physical component isn't a limitation, it's the learning advantage. Motor memory, spatial reasoning, embodied cognition create neural pathways that passive screen observation doesn't build. Your child who physically arranges command cards is simultaneously planning, executive function, predicting, spatial reasoning, encoding memory through multiple sensory channels. As your child grows, screen-free coding tools don't become obsolete, they become prototyping tools and conceptual references. My 11-year-old still pulls out her old Botley robot when debugging complex Python loops because watching the physical execution helps her visualize what the code is doing wrong. The screen time conversation we keep having as parents, how much is too much, what's educational versus merely entertaining, how do we balance digital skills with childhood, finds a practical answer in screen-free coding toys. You can say yes to computational thinking, yes to preparing your child for a technology-saturated future, yes to building skills that matter for AI literacy and digital fluency, all while preserving the physical play, face-to-face interaction, tactile exploration that childhood development needs. Your child doesn't need to choose between unplugged play and computational literacy. Screen-free coding toys deliver both, building the foundational thinking that makes every subsequent technical skill more accessible. Start with Sequence. Celebrate the first successful 20-step program. Notice when loop patterns emerge naturally in your child's thinking. Trust that the physical foundation you're building now will support increasingly sophisticated computational thinking for years to come. Thanks for listening to this episode of the STEM Lab podcast. We drop new episodes every Monday, Wednesday, and Friday, so you've always got something fresh coming your way. If you found this episode useful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It sounds small, but it genuinely makes a difference. That's how other parents who are looking for this exact information actually find the show. And if you haven't already, hit subscribe or follow so you get notified the second a new episode goes live. Thanks again, and I'll see you in the next one.